Practice problem on graphing motion. A graph of a car's motion along the road is shown. Describe the motion of the car, calculate any acceleration rates as well as the distance traveled, and also sketch the corresponding position versus time and acceleration versus time graphs. Let's first describe the motion of the car. Here we can see this is a velocity versus time graph. So we can see the velocity of the car is 12 meters per second, and it maintains that constant velocity of 12 meters per second for 4 seconds. The next thing we can see is the car decreasing its velocity over the next 3 seconds, as if it's putting on the brakes coming to a stop sign. We would say that velocity is decreasing, or it's a negative acceleration. So we can see there's two parts of motion of this car. From 0 to 4 seconds, it's traveling at a constant velocity, and then for the next 3 seconds, from 4 to 7 seconds, it has a negative acceleration, meaning its velocity is decreasing. So just as if the car was driving down the road at a constant velocity and then saw the stop sign up ahead and put on the brakes and came to a stop. So we can see from the graph that it did accelerate from 4 to 7 seconds, and went from 12 meters per second to 0 meters per second. Well, using the definition of acceleration, where it's the change in velocity over the change in time, we can see that that's the final velocity minus the initial velocity over the time. While the final velocity is 0, it was traveling at 12 meters per second before it put on the brakes, and it did that over 3 seconds. So we can see 12 over 3, or negative 12 over 3, is negative 4 meters per second squared. And again, all this means is that the car's velocity changed by negative 4 meters per second each second. So every second that went by, the car lost 4 meters per second of velocity. So if you look back at the graph, this negative 4 meters per second squared is actually the slope of the velocity time graph. Whereas if we take the area of the velocity time graph, that'll give us the distance traveled. But there's two different areas we need to take looking back at the graph. So the first part of that graph, it was going at 12 meters per second for 4 seconds. If we look at that, that's going to give us a rectangle here that we need to take the area of. So the area of our rectangle there is going to be length times width, or 12 meters per second times 4 seconds. So that'll give us 48 meters for the distance the car travels during that time of constant velocity here. Now we can look at the accelerated motion part of the graph, where it has a negative slope, and where it was going from 12 meters per second to 0 meters per second for 3 seconds. Well, that's going to make the shape of a triangle that we want to take the area of that. Now the area of a triangle is 1/2 base times height. So we see our base is actually the time, or 3 seconds, and the height will be 12 meters per second. Again, that's going to be base of 3 seconds times the height of 12 meters per second. So if we do out that math, 1/2 times 12 is 6, times 3 is going to give us 18 meters. So that just means then the total distance traveled here by the car during that whole trip is going to be the sum of those two, which is 48 plus 18, and that is 66 meters. Okay, so that leaves us with determining what the graphs are that match this velocity time graph. So remember the video on graphing motion, where it talked about what the slope represents for different graphs. So we're going to use that information to go to our position time graph from our velocity time graph, and then to our acceleration time graph from that as well. All right, so let's look at our distance time graph here, position versus time. And if you remember, the slope of a position time graph is the velocity. Because if we take rise over run, that will give us distance over time, and that's going to tell us about what our velocity is doing. So back to our velocity time graph, we saw that it was going at a constant velocity to start. We'll rewrite that there. And then the velocity was actually changing, and it was undergoing a negative acceleration rate. So we can see for the first 4 seconds our velocity is constant. So that means we need a constant slope on our velocity time graph for the first 4 seconds. So I did that here. This would be the 4-second mark there. And I tried to make that as constant slope as I could. So again, we have a nice constant slope and hence a constant velocity there to show that. Now our velocity is going to change. It's going to decrease, if you remember, by -4 meters per second each second. So if our velocity is decreasing, we need to show that our slope is decreasing as well. So we need to go from steep gradually to less steep. So I'm going to go from this steepness to making it less and less and less steep till I get to a slope of 0 right there. So again, here we're going from a great high slope and then less steep, less steep, less steep, less steep till I get a slope of 0 there. So this is going to show that my velocity is decreasing, and hence I have a negative acceleration rate. Again, it's all about what the slope's doing. Constant velocity, I have a constant slope. If I have a decreasing velocity, it's a negative acceleration, I need to have a decreasing slope to show that. Okay, so now we want to look at our acceleration time graph here. So let's remember back at our velocity time graph that the slope tells you about acceleration rates. So if the slope is constant, we'll have a constant acceleration rate. If slope is positive or negative, we'd have a positive or negative acceleration correspondingly. So if we look here, we have a constant slope of 0. So our first acceleration rate is 0. And then we have a negative acceleration rate, which you remember was -4 meters per second squared. So again, from the 0 to 4 seconds, our acceleration was 0. And let's show that up here on our graph. Let's say this is the 4-second mark right there. So from 0 to 4 seconds, our acceleration is always going to be 0. So we'll just make a nice solid line along the x-axis here to show our acceleration rate is 0. And then from 4 to 7 seconds, it's -4. So maybe -4 is right here on our graph. And so let's assume that that acceleration instantaneously goes from 0 to -4 for the next 3 seconds. Now we have all 3 of our graphs here. From our velocity time graph, we were able to make our position time graph, and we were also able to make our acceleration time graph. All 3 graphs look different. We have a nice constant slope here and then a decreasing slope. Here we have a constant slope and a negative slope. Here we have a slope of 0 and then another slope of 0, but that's -4 meters per second squared. They all look different because they're all graphs of different things. Remember, the slope of our position time graph tells us about velocity. So the slope's going to do whatever the velocity does. On a velocity time graph, the slope tells us about acceleration. So the slope does whatever the acceleration is doing. And for our acceleration time graphs, well, we're always having no slopes on there. We're assuming constant accelerations of 0 here and of -4 meters per second squared. Thank you for watching, and see you in class.